So this is my Module 3 on coding and path analysis, and I am Caitlin Rodgers. So, generalized linear models are more flexible than the general linear model and allow us to test more complex models. So the general linear model requires that y is normally distributed, however, models within the generalized linear model do not. So in this module, I will be running multiple linear regression models and compare them to path analysis, which is part of the generalized linear model. So in the GLM, we can test multiple regression, however, we have to test each part of the model independently. The problem with multiple linear regression is that we're missing the overarching effect of the model. So without testing that overarching effect, we do not take into consideration subsequent effects, so any attenuated relationships that result due to shared variance of predictors within the model are overlooked. Path analysis allows you to simultaneously test direct and indirect effects. And in path analysis, you're testing data a priori, so regression models are designed to fit the data. According to Alwyn and Hauser 1975, in path analysis, we can decompose effects into direct and indirect parts. Decomposition has 4 parts. So the direct effect of x on y, the indirect effect of x on y through an intervening variable, an unanalyzed component due to not knowing the direction of the path, so though path analysis is often proposed as causal, so we neglect this. And a spurious component due to x and y being caused by some third variable or set of variables in the model. When an intervening variable is added to the sequence, the direct effect, which operates via that variable, is removed from the coefficients of other variables in the model. So in this module, I ran 2 multiple linear regressions for paths A and B, as shown in this diagram, and 1 path analysis that runs all parts of the model simultaneously. I then compare the results from the linear models to the path analysis. In the total path analysis model, x1 is a categorical predictor with 2 levels, so group 1 and group 2. In order to include a categorical variable in a model, it has to be coded. So coding allows us to assign numerical value to categories, and in general, there are various ways that you can do this, but for multiple linear regression, dummy coding is often used. This is when you create levels within a variable and assign them a value of either 0 or 1, and there's a base level which you use as the comparison for all other levels. So the sum of the cross products of any 2 codes will equal 0. However, using dummy codes can produce problems when trying to interpret the effects of interactions. And additionally, it's often debated in the literature on whether or not dummy coding violates the assumptions of path analysis. So because of this, I decided not to use dummy coding, and I grouped my categorical predictor x1 in order to look at the differing effects of each level and their effects on the other variables in the model. So as you can see in my model, x1 is implicit because it's grouped as either group 1 or group 2. So essentially I ran linear models and the complete path analysis twice with each group in order to code the categorical variable x1. So x2 is a continuous predictor and an exogenous variable. An exogenous variable predicts other variables in the model, but its source comes from outside the model. x3 is an endogenous continuous variable, which is being predicted by x2, and an endogenous variable is a variable that's being predicted by another variable in the model, and y is the outcome variable, which is also endogenous. So first, I'm going to run through the analyses of multiple linear regression models and then compare these linear models to the total path analysis. So looking at this diagram, this is my linear model 1. I ran the effect of x2 on x3 with each group of xy, and I included the standardized betas here, but I'm going to now go through the analyses that I ran through R. So looking at the estimate column, you can see the standardized beta for each group, and I use standardized betas so I can compare the results of each model, and standardized betas are in standard deviation units. So looking at the p-values, p-value indicates that for both groups 1 and group 2 of the categorical variable x1, there is a significant effect of x2 predicting x3 at the p is less than 0.05 level. So we have 0 for both of those groups. And then looking at the interaction in the linear model, the interaction is not significant at the 0.05 level because it's 0.26. So this indicates that the relationship between x2 and x3 does not differ across groups of x1. So now moving on to linear model 2, I ran the effect of x3 on y for each group of x1. So here is just the diagram to show that and the standardized betas. And looking at the R output, as you can see, there's a significant effect for each group of x1 in the relationship between x3 and y, our criterion, with the p-value as less than 0.05 for both groups. And looking at the interaction, it is not significant at the 0.05 level. This indicates that the relationship between x3 and y does not differ across groups of x1. So I ran diagnostics to see if the linear models met the Gauss-Markov regression assumptions. Looking at the residuals versus fitted plots, we can see that we have independent residuals for each model as well as no issues with homoscedasticity. Looking at the normal QQ plot, residuals seem to be slightly skewed. Because of this, we should be cautious in interpreting the results of the model, or both models. So for the total path analysis, I used the SEM package in R to test all paths simultaneously. As you can see, for both groups of the categorical variable x1, x2 significantly predicts x3, and x2 and x3 both significantly predict the criterion y. So all these p-values are less than 0.05 in both groups. Additionally, looking at the effects of the interactions, none are significant at the 0.05 level. So the relationship between x2 and x3, the relationship between x3 and y, and the relationship between x2 and y all do not differ across groups of x1. So there are also multiple types of indices that we can use to see how well our model fits the data. Like I said before, in path analysis, we test models a priori. So chi-square is essentially a likelihood ratio test comparing your model to a fully saturated model. If all paths are included in the model, then the chi-square will equal 0. For both groups here, the chi-square equals 0, indicating that we have a model of perfect fit. So the CFI is a fit indice that measures how well your model fits the data. And generally, a good CFI ranges between 0.9 and 1. So since our CFI is 1, we can conclude that our model strongly fits the data. The standardized root mean residual, or SRMR, is an absolute measure of fit and is defined as the standardized difference between the observed correlation and the predicted correlation. Generally, a value below 0.08 is considered a good fit here. So I would conclude that we have a good fit for our model here based on the SRMR. So the root mean square error of approximation, RMSEA, is another measure of model fit, and here it's 0, which indicates we have very strong fit. So overall, our model very strongly fits the data. And path analysis functions under the Gauss-Markov regression assumptions. Therefore, the diagnostic plots for each individual paths that I went over earlier can be used to interpret the total model as well. So now looking at the total model that I ran using SEM functions in R, the boxes with the dotted lines indicate the relationships that were attenuated when they were run simultaneously in the path analysis. So that would be path B here and path C prime here for both groups. So because Y has multiple sources in path analysis, variance of Y is being explained by multiple predictors simultaneously, and therefore the coefficients get attenuated. As stated in Alwyn and Hauser 1975, when an intervening variable is added to the sequence, the indirect effect, which operates via that variable, is removed from the coefficients of other variables in the model, which you can see here through these attenuated effects. So as you can see, running path analysis takes into consideration both direct and indirect effects, whereas in multiple linear regression, the indirect effects would not be taken into consideration, and thus we would not be able to see the attenuated effects of the betas. So using path analysis allows us to test more complex models and analyze relationships that we would not be able to fully see in general linear models. Despite the benefits of all regression models, we should be cautious in designing and using them according to Friedman 1991, who suggests that regression models should not carry much of the burden in a causal argument and that they provide few real examples of validation of modeling assumptions. And this concludes my module. Thank you.